So we've seen that bushfires spread their heat mostly by radiation. And we've seen that you get about 75 kilowatts per square metre being put out. But that's how much radiation a fire is putting out. What we really care about is how much radiation is hitting something else nearby, and whether that's enough to set that something else on fire, or if that something else is you to burn your skin or whatever it might be. So we need to study how the fire spreads, and there's some rather neat mathematics behind this. So first of all, let's assume we have something like a bush or a small tree that's radius 1 metre and the usual temperature of a fire, and it's on fire. So let's assume that the heat is coming from the flames, not from the actual twigs of the branch, but let's assume that the flames are roughly spread over a sphere of radius 1 metre. In that case, we can use a Stefan-Boltzmann equation and put in the radiativeness, 0.9, area, pi r squared, sigma times t to the fourth, and it turns out to be about a megawatt of power. Okay, that's a lot of power. Just from one bush burning. It won't put out that much power for very long. Before very long, or the outside of the wood has all been combusted, and there's no more gas to come out from the pyrolysis. But for a short while, it's putting out a megawatt of power. That's, of course, the power it's putting out. How much do you receive if you're standing some distance away? So for this, we can use the inverse square law. Because we've assumed our burning source is spherical, the power will spread out in all directions until it hits something in a sphere. And each area on the sphere will receive the same amount of power. So if we're standing some distance d away from the fire, the total energy it's putting out, roughly 1 megawatt, is now spread over a sphere of radius d. So we're only going to get a small fraction of it. Most of it will go off in some other direction. Energy is conserved, so all the megawatt will hit somewhere on the surface of the sphere, but only a little bit of it's going to hit the part of the sphere where you are. So this is called the flux, which is the energy per unit area, compared to the power, which is just energy, no per unit area. So the flux is equal to the energy per unit area is equal to the power radiated, the megawatt, divided by the area of the sphere. So this is the energy hitting 1 square metre. If it's spread over 1,000 square metres, you get 1,000th part of the total power put out. So, for example, let's say we had our burning bush, we calculated earlier, and you were 10 metres away. Your power is going to be the total power put out, a megawatt, divided by 4 pi d squared, the surface area of a sphere of radius 10 metres, which comes out as about 800 watts. So if you're 10 metres away from a burning bush, 800 watts, what does that mean? Well, we know that sunlight on a sunny day is about 1,000 watts, so it's a bit less than sunlight on a sunny day. So it's definitely something you can survive, but you'll definitely notice it, especially if it's sunny at the same time. It's not enough to set anything on fire. The sun doesn't normally set bits of wood on fire when they're laid out in it, and this is less than that, but you'll definitely feel it.